Question 1. Beyond predictive performance metrics like accuracy, what other factors are critical for a holistic model comparison in MLOps before deployment? Option A. The programming language used to develop the model. Option B. Inference latency, computational cost, scalability, interpretability, robustness, and fairness. Option C. The number of lines of code in the model's training script. Option D. The popularity of the model's underlying algorithm on social media. The correct answer is inference latency, computational cost, scalability, interpretability, robustness, and fairness. Here's the explanation. Model comparison involves a holistic assessment considering various factors, such as predictive performance, inference latency, computational cost, scalability, interpretability, robustness, fairness, and overall business impact, not just accuracy. Question 2. Which online evaluation method allows for the most definitive comparison of different model versions, real-time performance, and business impact in a live environment? Option A. Offline evaluation on a held-out test dataset. Option B. Shadow deployment. Option C. Canary deployment. Option D. A/B testing. The correct answer is A/B testing. Here's the explanation. A/B testing involves deploying different models to distinct, randomly assigned user segments, allowing for direct comparison of their real-time performance, user engagement, and business impact in a live environment. It is described as the most definitive way to compare models in production. Question 3. What is the primary role of experiment tracking systems in facilitating model comparison? Option A. To automatically deploy the best performing model to production. Option B. To log and manage metadata about each model training run, including hyperparameters, evaluation metrics, and data versions. Option C. To convert models into a specific format for edge device deployment. Option D. To continuously monitor a single model's performance after it has been deployed. The correct answer is to log and manage metadata about each model training run, including hyperparameters, evaluation metrics, and data versions. Here's the explanation. Experiment tracking systems are tools that log and manage metadata about each model training run, including hyperparameters, evaluation metrics, data versions, and code versions. This is crucial for systematically comparing multiple models and reproducing results. Question 4. What is the primary benefit of achieving reproducible experiments in MLOps for team collaboration? Option A. It automatically generates new features from raw data. Option B. It ensures that different team members can easily reproduce exact findings and build upon existing models without, works on my machine, issues. Option C. It eliminates the need for any manual review of model performance. Option D. It guarantees perfect bit-for-bit identical results across all hardware architectures. The correct answer is it ensures that different team members can easily reproduce exact findings and build upon existing models without, works on my machine, issues. Here's the explanation. Reproducible experiments facilitate seamless team collaboration by ensuring that any team member can recreate the exact conditions and results of an experiment, overcoming environment-related discrepancies, and accelerating development cycles. Question 5. Which of the following is an essential component for logging and organizing all metadata associated with an ML experiment to ensure reproducibility? Option A. Git for code version control. Option B. Docker for environment isolation. Option C. An experiment tracking system like MLflow or AWS SageMaker experiments. Option D. Cloud object storage for raw data. The correct answer is, quote, an experiment tracking system like MLflow or AWS SageMaker experiments. Here's the explanation. Experiment tracking systems are specifically designed to log and organize all critical metadata for each experiment run, including hyperparameters, metrics, code versions, data versions, and environment details, which is central to achieving reproducibility. Git, Docker, and cloud storage are also important but serve different specific functions. Question 6. When an experiment tracking system logs metadata, which of the following is not typically captured to ensure reproducibility? Option A. The git commit hash of the code used. Option B. The specific Docker image tag or environment specification. Option C. The current market value of the company deploying the model. Option D. All hyperparameters and configuration parameters used. The correct answer is, quote, the current market value of the company deploying the model. Here's the explanation. Experiment tracking systems log technical details necessary for recreating an experiment, such as code versions, environment specifications, hyperparameters, and performance metrics. The company's market value is irrelevant to the technical reproducibility of an ML experiment. Question 7. What is the primary benefit of properly setting and managing random seeds throughout an MLOps pipeline? Option A. To introduce true randomness into ML experiments. Option B. To significantly speed up model training times. Option C. To ensure reproducibility and consistency of experimental results. Option D. To automatically select the best model hyperparameters. The correct answer is to ensure reproducibility and consistency of experimental results. Here's the explanation. Random seeds initialize pseudo-random number generators, making random operations like data shuffling, weight initialization, deterministic. This ensures that an experiment or training run can be precisely replicated, which is paramount for debugging, comparing models, and auditing in MLOps. Question 8. An ML engineer observes that their model's performance metrics, e.g., accuracy, F1 score, vary significantly between training runs, even when using the exact same code, data, and hyperparameters. What is the most likely cause of this inconsistency? Option A. Insufficient training data for the model. Option B. Hardware failures on the compute instances. Option C. Failure to set random seeds for various components, e.g., NumPy, TensorFlow, Python's random module. Option D. An incorrect model architecture that is inherently unstable. The correct answer is failure to set random seeds for various components, e.g., NumPy, TensorFlow, Python's random module. Here's the explanation. Varying performance with identical code and data is a classic symptom of unseeded random processes. Without fixed seeds, data splits, weight initializations, and other stochastic operations will differ in each run, leading to inconsistent results. Comprehensive seeding across all relevant libraries is essential for reproducibility. Question 9. For achieving comprehensive reproducibility in a deep learning model trained with TensorFlow on GPU, which of the following random seeds typically needs to be set? Option A. Only Python's built-in _random.seed. Option B. Only _numpy.random.seed. Option C. Only _tf random.set_seed. Option D. Python's _random.seed. NumPy's _numpy.random.seed. And TensorFlow's _tf random.set_seed. And potentially CUDA seeds for GPU operations. The correct answer is Python's _random.seed, NumPy's _numpy.random.seed, and TensorFlow's _tf random.set_seed, and potentially CUDA seeds for GPU operations. Here's the explanation. For full reproducibility in complex ML pipelines, especially with deep learning frameworks and GPUs, it's crucial to set seeds at multiple levels. Python's standard library, NumPy for array operations, the specific ML framework, e.g. TensorFlow, and potentially CUDA for GPU-specific randomness. Question 10. What is the primary motivation for implementing dataset versioning in an MLOps environment? Option A. To reduce the storage cost of large datasets by compressing them. Option B. To ensure strict data security and access control for sensitive information. Option C. To achieve reproducibility, auditability, and robust collaboration within ML teams. Option D. To automate the collection of metadata about data sources and schemas. The correct answer is to achieve reproducibility, auditability, and robust collaboration within ML teams. Here's the explanation. The overview states that dataset versioning is fundamental for achieving reproducibility, auditability, and robust collaboration. It allows pinpointing the exact data state for model performance, debugging regressions, and meeting regulatory compliance. Question 11. A data scientist is debugging a significant drop in model performance. They suspect the training data might have subtly changed. Which feature of dataset versioning would be most helpful in investigating this issue? Option A. Automated data cleaning scripts. Option B. Immutable snapshots and metadata tracking. Option C. Real-time data streaming capabilities. Option D. Integration with cloud object storage versioning. The correct answer is immutable snapshots and metadata tracking. Here's the explanation. Immutable snapshots create unchangeable records of the dataset's state. And metadata tracking stores information like source, creation date, and pre-processing steps. Together, these allow the data scientist to retrieve the exact data used for a past, well-performing model and compare it against current data to identify changes, which is crucial for debugging performance degradation. Question 12. Which of the following best describes the relationship between dataset versioning and cloud object storage versioning, e.g. AWS S3 versioning, in an MLOps context? Option A. They are interchangeable terms for the same functionality. Option B. Cloud Object Storage Versioning is a complete solution for MLOps dataset versioning, including lineage and metadata. Option C. Dataset versioning builds on low-level object storage versioning by adding higher-level semantic understanding, metadata, and lineage tracking. Option D. Dataset versioning is only for small, structured datasets, while object storage versioning is for large, unstructured data. The correct answer is dataset versioning builds on low-level object storage versioning by adding higher-level semantic understanding, metadata, and lineage tracking. Here's the explanation. As per the Comparison/Related Concepts section, Cloud Object Storage Versioning offers basic versioning for individual objects. Semantic dataset versioning builds on this by adding higher-level concepts like metadata, lineage, efficient diffing across many files, and dataset-level abstraction, making it a complete solution for MLOps. Question 13. What is the primary purpose of collecting experiment metadata in MLOps? Option A. To reduce the computational cost of training ML models. Option B. To automate the deployment of models to production environments. Option C. To ensure reproducibility, traceability, and effective management of ML experiments. Option D. To encrypt sensitive data used during model training. The correct answer is to ensure reproducibility, traceability, and effective management of ML experiments. Here's the explanation. The overview states that experiment metadata is crucial for understanding, reproducing, and managing the iterative process of model development, and that, without robust experiment metadata, ML development becomes a chaotic and unmanageable process, leading to issues with reproducibility, traceability, and collaboration. Question 14. An ML engineer is reviewing an experiment run and needs to verify the exact code that was used to train a specific model. Which component of experiment metadata would provide this information? Option A. Performance metrics. Option B. Artifacts. Option C. Code version. Option D. Input parameters. The correct answer is code version. Here's the explanation. The key features/component section lists code version as a reference to the exact version of the source code used for the experiment, typically a git commit hash, branch name, or tag, ensuring reproducibility of the training logic. Question 15. In a regulated industry, an organization needs to provide an immutable record of how a machine learning model was developed, including its data sources, code versions, and training parameters, for auditing purposes. Which MLOps component is explicitly designed to fulfill this requirement? Option A. A feature store. Option B. Experiment metadata. Option C. A model registry. Option D. A data lake. The correct answer is experiment metadata. Here's the explanation. The use cases section highlights auditing and compliance for regulated industries, stating that experiment metadata provides an immutable record of how a model was developed. By leveraging the detailed experiment metadata, organizations can demonstrate complete traceability from raw data to the deployed model, proving compliance with internal policies and external regulations. Question 16. Which MLflow component provides a centralized hub for collaboratively managing the full lifecycle of MLflow models, including versioning and stage transitions, e.g., staging, production? Option A. MLflow tracking. Option B. MLflow models. Option C. MLflow projects. Option D. MLflow model registry. The correct answer is MLflow model registry. Here's the explanation. The MLflow model registry is specifically designed for versioning, stage transitions, and managing the lifecycle of MLflow models, crucial for governance and MLOps best practices. Question 17. In MLflow tracking, where are metadata about runs, experiments, parameters, and metrics stored, distinct from the actual binary files like trained models or plots? Option A. The artifact store. Option B. The ML project file. Option C. The backend store. Option D. The model registry. The correct answer is the backend store. Here's the explanation. The MLflow tracking server consists of two main parts: the backend store for metadata, parameters, metrics, run IDs, and the artifact store for actual binary artifacts, models, plots. Question 18. A data scientist wants to ensure that their machine learning code, along with its exact dependencies and entry points, can be run reproducibly by anyone. Which MLflow component is best suited for packaging the code in this standardized way? Option A. MLflow tracking. Option B. MLflow models. Option C. MLflow projects. Option D. MLflow recipes. The correct answer is MLflow projects. Here's the explanation. MLflow projects provide a standard format for packaging ML code in a reproducible way, including dependencies and entry points, ensuring anyone can run the code with the exact environment. Question 19. What is the primary purpose of weights and biases, W&B, in the MLOps ecosystem? Option A. To provide a distributed training framework for deep learning models. Option B. To serve as a cloud-based data storage solution for large datasets. Option C. To offer a centralized platform for tracking, visualizing, and managing ML experiments. Option D. To automate the deployment of trained models to production environments. The correct answer is to offer a centralized platform for tracking, visualizing, and managing ML experiments. Here's the explanation. W&B's core value is bringing order and transparency to ML development by providing a centralized, cloud-based system to log everything relevant to an ML run, thus tracking, visualizing, and managing experiments. Question 20. Which weights and biases feature is specifically designed to automate the search for optimal model configurations using various search strategies? Option A. Artifacts. Option B. Reports. Option C. Sweeps. Option D. Tables. The correct answer is sweeps. Here's the explanation. Sweeps is described as a powerful hyperparameter optimization tool that automates the search for optimal model configurations using various search strategies: grid, random, Bayesian. Question 21. A data scientist wants to begin tracking a new machine learning experiment using weights and biases. Which W&B Python API call is typically the first step to establish a connection and create a new run? Option A. wandb.log. Option B. wandb save. Option C. wandb config. Option D. wandb.init. The correct answer is wandb init. Here's the explanation. The documentation states that the user calls wandb.init at the beginning of their script. This establishes a connection to the W&B cloud service and creates a new run. Question 22. What is the primary function of TensorBoard in the context of MLOps? Option A. To train machine learning models automatically. Option B. To manage and version control ML model artifacts. Option C. To visualize, debug, and optimize machine learning experiments and models. Option D. To deploy models to production environments. The correct answer is to visualize, debug, and optimize machine learning experiments and models. Here's the explanation. TensorBoard is an open-source visualization toolkit that provides an interactive web interface for understanding, debugging, and optimizing ML models by visualizing metrics, graphs, distributions, and other data generated during training and evaluation. It does not directly train, version, or deploy models. Question 23. An ML engineer wants to compare the performance of multiple training runs with different learning rates and batch sizes. Which TensorBoard dashboard is specifically designed for this purpose? Option A. Graphs dashboard. Option B. Projector dashboard. Option C. HPARAMS dashboard. Option D. Images dashboard. The correct answer is HPARAMS dashboard. Here's the explanation. The HPARAMS hyperparameters dashboard is specifically designed to facilitate the comparison of different hyperparameter configurations, allowing users to analyze how varying hyperparameters impact model performance metrics across multiple experiments. The graphs dashboard shows model architecture, projector visualizes embeddings, and images displays visual data. Question 24. How does TensorBoard acquire the data it visualizes from an ongoing or completed machine learning experiment? Option A. It directly integrates with the model's memory to pull real-time data. Option B. It reads summary data from event files written to a specified log directory by ML frameworks. Option C. It queries a central database where all ML metrics are stored. Option D. It intercepts network traffic from the training script to infer metrics. The correct answer is it reads summary data from event files written to a specified log directory by ML frameworks. Here's the explanation. TensorBoard operates by monitoring a specified log directory for event files, which contain serialized summary data, scalars, graphs, histograms, etc., written by summary writer objects from ML frameworks like TensorFlow or PyTorch during training. It then parses and visualizes this data. Question 25. What is the main objective of implementing a training pipeline in MLOps? Option A. To manually execute model training steps one by one. Option B. To automate the end-to-end process of data preparation, model training, evaluation, and registration. Option C. To provide a graphical user interface for data visualization. Option D. To solely monitor the performance of deployed models. The correct answer is to automate the end-to-end process of data preparation, model training, evaluation, and registration. Here's the explanation. The overview states the primary purpose is to transform raw data into a validated, production-ready model artifact by automating the entire process from data ingestion and pre-processing through model training, evaluation, and registration. Question 26. Which component of an MLOps training pipeline is responsible for defining, scheduling, and managing the execution order of its various steps? Option A, model registry. Option B, data ingestion module. Option C, orchestration service. Option D, monitoring and logging system. The correct answer is orchestration service. Here's the explanation. The key features, components, section defines orchestration as the mechanism that defines, schedules, and manages the execution of the various steps within the pipeline. Question 27. How are the individual steps or tasks within an MLOps training pipeline typically structured and executed? Option A, as a linear sequence of manually triggered scripts. Option B, as a directed acyclic graph, DAG, defining dependencies and automated execution flow. Option C, as independent, unlinked processes run in isolation. Option D, as a single, monolithic script without distinct steps. The correct answer is as a directed acyclic graph, DAG, defining dependencies and automated execution flow. Here's the explanation. The How It Works section explicitly states that a training pipeline typically operates based on a directed acyclic graph, DAG, structure, where each node represents a specific step or task, and edges define the dependencies and flow of data/artifacts between steps. Thanks for watching. Please subscribe to my channel.